We're going to be looking at series, specifically arithmetic series. So what's the difference between a series and a sequence? Well, a series is just a sequence, except instead of commas, we now have addition signs. So what we're doing then is we're basically taking all the terms in a sequence and adding them together. Again, you can do this with a geometric or an arithmetic series, or sequence, I should say. Either type of sequence can become a series. So let's just dive right in. Actually, before we dive right in, we do need to address a new type of notation, just called sigma notation. So for instance, let's say I have an arithmetic series that goes 3 plus 5 plus 7 plus 9 all the way to term 10. So where this is term 1, and hopefully you can see your common difference is 2. So there's a way to express this using sigma notation or summation notation. And it's very fancy. You can think it might look scary to you, but just think of back to the first time you saw some fancy way of writing domain or range. You might have looked at it and panicked a little bit, but now your old hands at it. Like it's easier for you to read those domain and range notations, just like it'll be easy for you to read this notation. So the first thing is this giant symbol right here. All that means is sum. Okay, you'll notice that there is some number at the bottom and some number at the top. The number at the bottom refers to the variable that's going to be in our general equation, and it tells us where we start. So we're starting with n equals 1. In this case, we're starting with term 1. Okay, that's what it means in this specific context. And the number at the top tells us how far we go. Okay, in this case, because it says 10, we're going to term 10. Then right beside the summation notation is going to be some equation or expression. It's better to call it an expression because it's not an equal sign. It's some expression that models the series that we're talking about. So that 2n plus 1, you might ask yourself, okay, where did that come from? Well, all that came from was just taking this and finding the general term for it. So remember, Tn is equal to T1 plus n minus 1 onto D. So Tn in this case is going to be 3 plus n minus 1. My D is going to be 2. So 3 plus 2n minus 1, or 2n plus, oh, that should be a 2 there. 3 plus negative 2 is 1, and so that's just what Tn is equal to. And lo and behold, that's what we have written right there. Okay, so that's how we read this right here. Basically, all this is saying is sum the first 10 terms of a general, of a series that is modeled like that. Of a sequence that's modeled like that, I should say. And if you were to actually expand it out, this is what it reads as right here. So you start with your 2n plus 1, and then you substitute 1n plus sign, substitute 2n plus sign, all the way till you substitute the 10n. Okay, now you can do this by hand. This one isn't too bad, right? Like you could say, 3 plus 5, well, I'm going to have to add 2, and then add another 2, and then add another 2. So how many terms do I have? 1, 2, 3, 4, 5, 6, 7. Got to keep going there. Plus 17, plus 19, plus 21. Oh, do I have enough? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Beautiful. So I have my 10 terms. Then I'd have to actually go 3 plus 5 is 8. 8 plus 7 is 15. 15 plus 9 is 24. And then what is that? 35, 45, 48, and so on. Okay, so this would, in this case, this would be doable. But imagine trying to do this for, instead of just the first 10 terms, the first 100, the first 1,000. Is there an easier way to do this? And luckily there is. And we're going to do a little quick history lesson here by by a famous mathematician called Frederick Gauss there. Okay, so when Gauss was, 10 years old in math class, or, a little math room or whatever they did back in the 1600s, he was a cheeky kid. He was a smart guy, and he was ahead in his homework or ahead in the class and being a little bit disruptive. So the teacher just went up and said, hey, I need to keep you busy. You're going to add all the numbers from 1 to 100. And the teacher walks away, and figuring, that would have gained them, a couple of minutes of peace and quiet, maybe an hour. Well, Frederick Gauss here is a smart kid, and he actually figures out a pattern. He sees a pattern and a quick way to actually do this. And what Frederick notices is that if, he's got to add from 1 to 100, if he actually writes the end of the list here, going backwards, he sees, did I count right? This is a 98, that's a 97, I can count backwards. He sees a pattern. He sees that 1 plus 100 gives us 101. Oops. 2 plus 99 gives us 101. 3 plus 98 gives us 101. So Frederick says, aha, there's a clear pattern in this. And that's all math is at the end of the day, is just seeing or finding some more efficient way of doing things through a pattern. What he can do is he knows that every single term, if he matches it up with its counterpart at the end of the list, gives him the same constant amount. So if he knows what to multiply then, well, all he has to do is take 101, times it by the 100 terms in the list, and if he does that, he's going to get a value that's twice the amount, right? Because like he's basically has two lists going on. He has the 1 to 100 and then 100 to the 1, okay? So if he times it by the 100 terms, he's going to get a value that's 2 times as much because he's not just adding one list, he's adding two lists now. So he times it by 100 and then he divides by 2 to get his final answer. Okay, I think it gives us 5,050 or something like that. So that right there is the expression, the equation, to actually find the sum of a series. If we know the first term and we know the last term, all we need to do is multiply by the number of terms in the series divided by 2. Okay, so let's say I have 7, 14, 21, 28, and I want to sum to 34. Well, first thing I need to do, if I'm looking at this, is I need to figure out what that term 34 is. Okay, what is term 34? So I'm going to find it out by using this little equation right here, which you should remember from the previous video. So I see that my common difference here is 7. So I can say, okay, Tn then is equal to 7 plus n minus 1 with a common difference of 7. So Tn then is equal to 7 plus 7n minus 7, or Tn is equal to 7n. Okay, nice and easy in this case. So term 34 then, term 34 is just going to be equal to 7 times 34. I'm cripplingly lazy, so I'm just going to leave it as 7 times 34. And I'm going to figure out, okay, the sum of the first 38 terms then is equal to 38 over 2, 7 plus 7 times 34, like that. And I guess I've got to write it out here. So I've put off having a calculator in the hopes that I wouldn't need one, but here I do. So 7 times 34 plus 7 times, I put 38, but I should say 34. Gesundheit. 34, 34, and then I'm going to divide that by 2, which gives me the sum of the first 38 terms is 4,165. Okay, imagine trying to do that by actually going 7 plus 14 plus 21, okay? And by the way, I can recreate what Frederick had there because we know that the first term is going to be 7, and then 14, and then 21. And since we know we end with, what was 7 times 34? 7 times 34 gives us 238. So we end with 238. If I minus 7 from that, we get 231. I minus 7 from that, we get 224. And if I actually sum these together, so 238 plus 7 gives me 245. 231 plus 14 gives me 245. 21 plus 224 gives me the 245 again. So all we're doing is we're taking 245, multiplying it by 34, and then dividing by 2, because again, we have two lists here, whereas we should just have one. So some of you might have noticed that, hey, is there a way for me to combine, like if I see Tn here and I have an equation Tn, could I just combine them together? And the answer is, of course, yes. So because Tn is also equal to this right here, is equal to that, then we can substitute this into the equation. And we can simplify just a little bit because you'll notice you'll see 2 T1s. So you can just have the 2T1 right there as an abbreviation. You could multiply the d in. It's usually not done like that because it's better just to multiply by d once after subtracting the difference between n and 1 and then continuing on. So let's just try that on for size. So practice sum of the first 20 terms. So the sum of the first 20 terms is going to be equal to, so I've already messed up there. Got to do the division. So I'm going to go 20 divided by 2. 2 times 30, close, plus, and then it's what's going to be, so 20 minus 1. And my common difference is minus 4, close that. And so I'm going to have 10 onto 60 plus 19 times negative 4. And let's see if I can't do that. So 19 times -4 plus 60 gives me -16, 10, and then it's not done. That's what happens when you write with one hand. And so that'll give me -160 is the sum of the first 20 terms, which might seem a little low, but you'll notice that, like, if you think about this list, there's going to be a significant portion of it that's positive and a big portion that's negative, and a slightly bigger portion that's negative. So some of those positives cancel out with some of those negatives, which means we're going to get a number that's closer to 0 than perhaps you would think if you're summing 20 terms in a series. Similar thing's going to happen here, but it's going to be less exacerbated because we're starting pretty close to 0. So I'm going to sum to the first 20. That's going to be equal to 20 over 2. And then 2 times -10 plus 20 minus 1. My common difference here is a +6, I believe. Yep. So 6. So sum of the first 20 is going to be equal to 10. -20 plus 19 times 6. And that's going to give me what? So 19 times 6 gives me 114. So 10 times -20 plus 114. So minus 20 from that. And then times 10 gives me 940. 940 as the sum of the first 20 terms. Okay. Determine what term you need to sum to have a sum of more than 500. Okay, interesting. So I know I want to have more than 500. So what term do I need to sum to? So let's write out that equation there. And let's think about what this is asking us. So n over 2, and then 2t1 plus n minus 1 d, close brackets. So I want my sum to be more than 500. So I'm going to write 500 here. And whatever's on the right side, I want to be a bigger number. Okay, I don't know what n is. That's what I'm looking for. I'm looking to find out what term I go to. 2 times, I do know what t1 is right here. So it's just -25. So -25, close. Plus, again, I don't know what n is. So I'm just going to leave it as n minus 1. And I do know my common difference. It looks like it's +6. So 6, then close brackets. This is just an inequality of two variables. So this will be pretty straightforward. So I've got 500 less than n over 2. This will give me -50 plus, and then I'll distribute that 6n, so I'll get 6n minus 6, and then I'll simplify inside, so 500 less than, and then I'm going to get n over 2, and then what's that going to give me? So 6n, -50 minus 6 is -56, close. I'll distribute that n in, so 500 less than, n over 2 times 6n is going to give me 3n squared minus this 56 divided by 2 will give me 26. Nope, 20. Jeez Louise. What's 56 divided by 2? Why am I having a brain fart here? 56 divided by 2 is 28. There we go. 28. 28n. And then hopefully you can see that this is a quadratic now. So I'll just subtract 500 from both sides. So 0 then has to be less than 3n squared minus 28n minus 500. Now, there is no guarantee that this is actually going to be a factorable equation, right? Because I might end up with some value like 17.4. So what that means is, because n can only be a natural number, I would have to say you've got to go to the 18th term, okay? Because if I went to the 17th term, it would end up being a little bit less than 500, but I want something more than 500. So you're always going to end up with situations like this when you're doing these sorts of questions with some great big weird quadratic. The process is going to be to use quadratic formula, okay? I mean, if you want to, you could try factoring out a 3. You're thinking to yourself, okay, can I multiply to get -1500 and add to get -28? You're going to have times where that does work, but it's going to be a much more efficient, just on the long run because of the size of these numbers, to use quadratic formula. Or, a technology if you have Desmos at hand, just plop it into Desmos. So I'm going to go -28 plus minus the square root of b squared, so -28 squared minus 4, 3, -500, all over 2 times 3. So I'm going to have 28 plus minus the square root of, let's see if I can't do this in one shot, so 28 squared plus 4 times 3 times 500, 500, not 0. It's going to give me 6, 7, 8, 4, all over 6. So there's going to be two roots, one positive, one negative, but you have to remember that your n has to be, remember this is, we're always thinking what n is equal to, n is equal to. So your n has to be a natural number, so the negative won't make sense, and the decimal will be rounded up. So the square root, so do I have a square root button? Yes, I do. So second square, second answer gives me 82. So I'm going to do 28 plus 82.3 divided by 6, and then 28 minus 82.3 divide by 6. The minus, the negative root, does not make sense, okay? It does not exist. We do not have negative natural numbers. So this one, 28 plus 82.3 divided by 6, gives me a number of 18.38. I can't have an irrational or even just a regular rational number that's a decimal with n. So then I have to say I have to sum to the 19th term to get a number bigger than 500. Okay, these are all going to be the same. If you get a question like this, it's always going to be the same beats. You're going to end up with a quadratic. You're going to use quadratic formula, and then you're going to pick the positive root, and then you're going to round the positive root up if it's a decimal. Or even if it's a rational number, even if it was like 18.2 ended, you'd still have to round up because n has to be a natural number. So next thing, determine the number of terms in the series. So this is exactly like the one up here, except you're going to end up with a situation where it's going to be factorable because you're going to get a whole number out. You can still use quadratic formula if the terms are unwieldy, but it's going to be the exact same mouthfeel, except you're going to have an equal sign, okay? So I'm not going to bother doing one of those.